My plan for today is just to talk about power series again. And power series is supposed to be introduced as part of the standard Calculus 2 curriculum. So I hope you guys have seen power series before. We are going to use power series in our differential equations class next time we meet on Monday. So this is supposed to be a review just to catch you up. It's supposed to be a scaffolding lecture. So to remind you of some definitions, a series is the limit of the sequence of partial sums of another sequence. So this is what a partial sum looks like. A partial sum is what you get if you are adding up the terms of a sequence as you go. So if your sequence was, for example, 1, 2, 3, 4, and so on, then your partial sums would be what? 1. And then 1 plus 2 is 3. And then 3 plus 3 is 6. And then 4 plus 6 is 10. And so on. So the partial sums are just adding up all of the terms of your sequence so far. And the series is what happens if we take the limit as n goes to infinity of the sequence of partial sums. And to shorten the notation, we write it as an infinite sum. It's the plus infinity as the upper bound here. We say that the series converges if the limit exists and it remains finite. If the series does not converge, we say it diverges. So what about the series I just wrote down? This sequence of partial sums, does this limit exist as n goes to infinity? This diverges as n approaches plus infinity. It diverges to infinity, so you could say the limit exists, the limit is plus infinity, but we still say that this diverges because it doesn't remain finite. Okay, so one of the first series we talk about in Calculus 2 is called the geometric series. And the geometric series looks like this. We're adding up all of the powers of r, starting with r to the 0 power plus r to the 1 power plus r to the 2 power, plus r to the 3 power, and so on forever. It turns out if r is 1/2, for instance, this would be like 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on forever. Do you know what this adds up to? Two. Yeah. You never quite reach 2 with any of the partial sums. But as you continue to add more terms, you're getting closer and closer and closer to 2. So if we plug in r equals 1/2, we get the number 2. The way you could evaluate a geometric series for other values of r would be like this. I'm going to call my series S. So that way s is equal to 1 plus r squared plus r to the third, and so on. And then I'm also going to consider what it would look like if I multiplied my entire series by r. Well, then I would have r plus r squared plus r to the third, and so on forever, right? And then what would it look like if I took s minus r times s? What happens if I subtract those two series?
You just get 1?
Yeah. Specifically, if you wanted to be a little bit more rigorous about this, we could say, consider what happens if you take the nth partial sum of both, right? And then you'd have the 1, and everything would cancel except for the minus r to the power capital N plus 1 or something like that. So to get the series that results from the difference here, I would want to take the limit as n approaches infinity of 1 minus r to the n plus 1. And this is equal to 1 if the absolute value of r is less than 1, right? Because if r is anywhere from -1 to +1, that means this absolute value is less than 1. Raising this to an power n plus 1 as n approaches infinity is actually going to shrink this term to 0, and all you're left with is the 1 in the limit. But if the absolute value of lowercase r is greater than 1, like if it was a 2, then taking the limit as n approaches infinity of 2 to the power n would be like a number that diverges, right? It grows to infinity. And of course, if it was negative, it would still diverge and grow larger and larger, but it would oscillate in sign because raising a negative to a power oscillates plus and minus sign. So it's going to diverge for the absolute value of r greater than 1. What happens if r is exactly equal to 1? Yeah, I guess so. And then what happens if r is equal to -1? Then it would diverge, right? Because it would oscillate between positive and negative sign. It would oscillate between 0 and 2. Okay, so we figured this out. We have just decided on what is s minus rs. And so let's take just the first case and say s minus rs is equal to 1. And then solve for capital S. And this is how we evaluate a geometric series. You tell me a value of lowercase r, between -1 and +1, and I can tell you what the geometric series converges to by taking 1 divided by 1 minus r. I wonder what happens in that third case where we said that this limit is 0 if r is equal to 1. Well, if r is equal to 1, then s minus s is equal to 0, and this tells us nothing. The real result of this series, if r was equal to 1, would be like 1 plus 1 plus 1 plus 1 plus 1, and then it diverges, right? So it looks like this geometric series is going to diverge everywhere except where absolute value of r is less than 1. And where it does converge, it's going to be evaluated like this. Okay. So now let's talk about power series. A power series is a function like f of x equals, and then you've got a series, and every term in the series has an increasing non-negative integer power of x minus c. That lowercase c is called the center of the power series, and then they all have a coefficient that goes in front of the factor x minus c to the n. When you want to evaluate this function f of x, you come up with a real number x where you want to evaluate the function. You just plug it in where the x is, and then you take the limit of the sequence of partial sums just like you normally would for a series. And just like before, we say a power series converges at the point x if this limit exists and it remains finite, and if it doesn't converge, then we say it diverges. So every power series belongs to one of 3 possible categories. Some power series will converge only when x is exactly equal to c. And this is a really, really boring case because then every factor that has x minus c will just be 0. And so the power series is just equal to its constant term at the point x equals c, and it diverges everywhere else. So that's a super boring case. The second case is if it might converge for any and every value of x. We can come up with some power series pretty easily that converge for any value of x you choose, even if it's a trillion or negative a trillion. The third case is it converges if and only if x belongs to some interval with a center of c and a finite radius of convergence rho. And another way to say this, another way to tell you about the same exact 3 cases, is you could say that every power series converges on some interval with center c and radius rho, but the 3 cases are, well, maybe your radius of convergence is 0. That would indicate it converges only when x equals c. Maybe your radius of convergence is infinity, and that would converge for any and every value of x. Or maybe your radius of convergence is a finite real value. This interval could be open, or it could be closed, or it could be half open and half closed on, one end of the interval. That's not really what we're concerned with in differential equations. We say a power series converges absolutely. And what makes this absolutely is in this limit, do you see I've added absolute values? That is the absolutely part. So we say it converges absolutely if we can add absolute values on every term, and it still converges. And if you remember way back to your Calculus 2 days, there are some series that converge, but they don't converge absolutely because there's an alternating series test that's a little bit more generous and forgiving than the other convergence tests for power series. or for series in general. So in other words, if a power series converges absolutely, then it converges. But if it converges, that doesn't necessarily mean that it converges absolutely. So converging absolutely is a stronger requirement. Prove that if a power series converges at a point x, or x0, then it must converge absolutely for every point x where the distance along the real number line from x to c, the center of the power series, is less than the distance from x0 to c. Another way of saying this, what I'm trying to claim here in exercise 2, is that the only thing that matters in terms of determining where your power series is going to converge is how far you are away from the center of the power series. If you're close to the center, you'll converge. If you're far away from the center, you might diverge. But we don't have to worry about multiple intervals of convergence. There's only going to be one continuous interval of convergence, is what we're trying to claim. And so I typed out the proof this time because I wanted to save class time. I think there's a lot we need to get to, but this is what the proof would look like. We say, since the series converges when I plug in x0, then the limit of the terms have to be 0. Right? Like if the terms themselves in the series are not converging to 0, then there's absolutely no way their sequence of partial sums can converge to 0. Every convergent sequence is bounded. What that means is like there has to be a maximum value of the terms in the sequence if it converges to 0 over time. Don't know what that is necessarily, but there has to be some maximum. And so we'll say that the absolute value of any given term in that sequence has to be less than or equal to capital M, where capital M represents the absolute value of the maximum term. Then we consider any point that is closer to the center than the point x0. And the difference here is that instead of looking at x0, we're looking at just plain x. And what this implies for the right side of this inequality is that I'll try to show you. I'm going to color code this better. What this means for the right side of the inequality is if I take this and I multiply both sides by x minus c to the power n, and then divide both sides by x0 minus c to the power n, that's how we get to this point. Then you can define a number lowercase r, and that number lowercase r is just going to be this ratio on the right-hand side of my inequality, x minus c divided by x0 minus c, absolute value. And notice, because x is closer to the center than x0 is, this number, this ratio is between 0 and 1. And so I can say that a particular term of my power series has an absolute value that's less than or equal to capital M times lowercase r to the n, where lowercase r is between 0 and 1. Because m is a constant, I can take an infinite sum of both sides here and then remove the constant outside of the sum, right? That's just factoring out the capital M constant. But this is the important part, that on the left side, this series, if it converges, would mean that my power series converges absolutely at the point x. And on the right side, this is a geometric series. And this geometric series converges because r is between 0 and 1. And since we just showed with this argument, this less than or equals to inequality argument, that the left side is less than or equal to the right side, and the right side converges to a finite value, that means that the left side also has to converge to a finite value. So that's how we know that power series have a single continuous interval of convergence. You don't have to worry about maybe it converges here, maybe it converges here, and maybe it doesn't converge in the middle. That can never possibly happen. If you were asked to prove that if a power series diverges at a point x0, then it must diverge for all x such that the distance from x to the center is greater than the distance from x0 to the center. This proof is really easy. You just say, I can find a contradiction. Suppose that the power series did converge at a point x that's farther from the center. Then, if it converges at x, it would have to converge at the point x0, because it converges at all points closer than a point you find that converges. And that's a contradiction to our hypothesis, because in the hypothesis we said a power series has to diverge at a point x0. So very short, sweet, easy proof there to get the converse. And so we get this picture of like, here's my real number line. I choose a point that's going to be the center of my power series. And along this green interval, every single point along the real number line is going to let my power series converge absolutely up until I reach the center of the series plus the radius of convergence, or the center of the series minus the radius of convergence. And outside the interval, I know my power series is going to diverge, both on the left side and the right side. And at the endpoints, we actually don't know. This is not a big concern for us in differential equations. In calculus 2, I would probably have the students test whether the power series converges at the endpoints. But it might converge, it might diverge. It doesn't have to converge absolutely, but it could still converge possibly. Things could be different at the endpoints. But at least we know what happens inside and what happens outside of that interval. So really quick, if I have two power series, I can add them together term by term. So if I add the coefficients of two power series, and I know that these two power series converge, then this is also going to converge when I just add the coefficients. The same thing happens when I subtract, because those coefficients are allowed to be positive or negative anyways, so subtracting is like adding a negative. You could multiply two power series together. But if you're multiplying power series, it's important to remember that you can't just multiply the coefficients term by term. That's not how multiplication works. It's a lot uglier and messier. If I say that the new coefficient is going to be lowercase pn, then calculating that pn coefficient is actually the sum of the products of a bunch of different a and b coefficients. You can also divide power series, but that doesn't happen term by term either. I'm not actually going to make you do this. I'm not going to make you multiply or divide power series. I just need you to know that you can't just take the corresponding coefficients and divide them and get your result. It's more difficult than that. Also important to know is that if you are adding, subtracting, or multiplying power series, the power series you get as a result is going to have a radius of convergence that's at least as large as the smaller radius of convergence of the two power series that you're adding, subtracting, or multiplying. That's not true if you're dividing. The quotient of dividing two power series could have a radius of convergence that's smaller than the smaller of the two, numerator and denominator. You can take derivatives of a power series term by term. And so if I had a function that's defined by some power series and I want to take the derivative, it's actually pretty easy. You could just look at every single term individually and do the derivative power rule. Like, what's the derivative with respect to x of an times x minus c to the power n? So you bring down the n, you keep the an because it's a constant multiple, and I would have x minus c raised to the power n minus 1. So now think about this. If I start off with my index variable here, down here as n equals 0, the first term is going to be 0 times the rest of this stuff, right? So I don't even need the term that starts with n equals 0. This is exactly the same as the series that goes from n equals 1 up to infinity. And then I want to do one more thing to this series before I move on. And that is, it's going to be really useful to us next week if our x minus c factor is raised to the power n instead of n minus 1. And so I'm going to make a little redefinition of what this index means to us. We're going to replace every n with n plus 1. So where I wrote n equals 1, I need to replace this with n plus 1 equals 1, right? Go ahead and do that really quick. I'm going to change my color to orange. I'm replacing every n with n plus 1. Like that. And my index variable was kind of arbitrary anyways, like how I want to number things is up to you. So it's okay if I do this, as long as I'm consistent about it. The consistency is the important part. I have to do that for every single n. And then one more little step and then we'll be done simplifying this thing. My f prime of x power series is going to be the sum from something to infinity. If I look at this n plus 1 equals 1 equation and I subtract 1 from both sides, what do I get? N equals 0 And then I have n plus 1 times a n plus 1 times x minus c. And then what's n plus 1 minus 1? N. So that's what I want to see, because as we solve some differential equations using power series, one of the things we're going to have to do is make sure that we have x raised to the n power. And that's how you do it after you take a derivative. F of x has x to the n power. Taking the derivative makes it x to the n minus 1 power. And so you've got to do some fancy math rearranging to make it x to the n power again. So we can do this with the second derivative as well. It's the same procedure. We would just say f double prime of x is what I get if I take the derivative term by term. And so that's going to be n equals 0 raised to the power infinity. The second derivative is just the derivative of the derivative. So I would look at I would go ahead and look at what we wrote down in this green box to start from. And so imagine looking at this term that has n plus 1 times a n plus 1 times x minus c to the power n, and take the derivative with respect to x. What's my derivative? Yeah. N times n plus 1.
Yeah, times a of n plus 1 times x minus c to the n minus 1.
Perfect. And then we realize what happens for the very, very, very first term in the series when n is equal to 0. That n is 0, right? So I don't need the first term. I could get rid of that one and start at n equals 1. And then the next step is going to be doing in orange exactly what we did in orange above. We're going to replace every n with n plus 1. So I'll write n plus 1 equals 1. N plus 1 plus 1 times n plus 1 times a subscript n plus 1 times x minus c raised to the power n plus 1 minus 1. And you're allowed to do this as long as you are very consistent about replacing every single n with n plus 1. And then we can finally simplify all of this and say, well, the equation down below the sigma says n plus 1 equals 1. That means n equals 0 is where I start. And then n plus 1 is n plus 2 times n plus 1 times a subscript n plus 2 times x minus c raised to the power n plus 1 minus 1. That's my second derivative. Okay, questions? Cool. You can also take antiderivatives of power series on a term-by-term basis. You don't have to worry about any kind of weird, cross-term stuff, because derivatives and antiderivatives are linear operators. They work on each term individually. They have the additivity property. But this is going to be important next week. The reason this is important next week is we're going to have second order ODEs that have the second derivative of a function and the first derivative of the function and the function itself in the ODE. And what we're going to do is we're going to replace the function with a generic bland old power series like this. And we're going to replace the first derivative of that function with this power series. We're going to replace the second derivative of that unknown solution function with this power series. And then we'll be able to find our solution as long as we can solve for these coefficients. And that's the secret or the trick behind power series solutions. And by the way, taking a derivative or an antiderivative does not change the radius of convergence at all. There's a pretty quick and easy proof, but I want to make sure we get through the rest of the notes in class. If a function may be represented by a power series with a non-zero radius of convergence, right? Like we want it to not be a boring power series, but it actually does have some kind of interval where it converges. Then we say the function is analytic. If you ever hear about an analytic function, it's just a nice, well-behaved function that can have its own power series somewhere. If an analytic function has a radius of convergence infinity, then that function is entire. So entire is an adjective that we use to describe functions that are analytic everywhere. So it turns out that there's a bunch of entire functions that you're already familiar with. Every polynomial is entire because a polynomial is its own power series, and obviously is defined on every real number. Sine and cosine are entire functions. E to the x is an entire function. There might be more, but I'm blanking. Other functions you're familiar with might be analytic, but they're not entire functions, like natural log, for example. It's not defined on the whole real number line, right? It's only defined for positive real numbers. So while a natural log is an analytic function, it can be defined with a power series. It has to have some finite radius of convergence. The same thing for rational functions. Those would be analytic, but not entire. The same thing for tangent, because there's places on the real number line where tangent has vertical asymptotes. That would be analytic. We can describe tangent with the power series, but the radius of convergence is going to be limited. We can find the power series corresponding to an analytic function using the Taylor series formula. This is, again, something I hope you saw in Calculus 2. So every function is equivalent to a power series where the coefficients of that power series correspond to the derivatives of the function evaluated at the center divided by n factorial. And if you set the center of the power series to 0 in the Taylor series formula, we call it a Maclaurin series. So if I wanted to, I could find the Maclaurin series of e to the x. Because what's the derivative of e to the x? Yeah, and that's true for every derivative of e to the x. That's what makes it really easy. What if I wanted to take e to the 0 power? It's 1. What if I wanted to take f prime of 0? Oh, it'd still be 1. Or f double prime of 0. It'd still be 1. And this is true for every derivative of e to the x. And so if I let 0 be the center of this series, it makes it a Maclaurin series. And then using this Taylor series formula, we would say that e to the x is equal to a power series where every coefficient looks like 1 divided by n factorial times x to the power n. Again, the reason for that is because every derivative of e to the x is e to the x, and then when I evaluate that at 0, I get 1. I divide by n factorial, and then when I take x minus c, we take x minus 0 to the power n, right? It's our Maclaurin series for e to the x. I think one of the coolest demonstrations, and hopefully you've already seen this, but one of the best things you can do in Calculus 2 is this. Okay, in red, that's my function e to the x. In blue, that's partial sums of my Taylor series. So the Taylor polynomial of degree 1. And then as I increase the degree of the Taylor polynomial, right, increase the degree of the number of terms I'm adding up in my Taylor series, you can see that it's matching closer and closer to the function over a larger interval. And if I let this become really large, you can kind of tell that in the limit as n approaches infinity, I'm going to get exactly the right function back. What else? We get, what about this one? 1 divided by x plus 1. This is a favorite example of mine in Calculus 2 because I could write it as 1 divided by 1 plus x. And then you remember how to do polynomial long division? You can write 1 divided by 1 plus x like that. How many times does 1 go into 1? And then I write this, and I subtract it. How many times does 1 go into negative x? Negative x times, yeah. So when I multiply negative x times 1 plus x, I'm going to get negative x minus x squared. The negative x's cancel and I get plus x squared. And then I ask myself, how many times does 1 go into plus x squared? Plus x squared, yeah. So I multiply plus x squared times 1 plus x, and I get x squared plus x cubed. Subtract, the x squareds cancel, and get minus x cubed. How many times does 1 go into minus x cubed? Negative x cubed. So I multiply negative x cubed times 1 plus x. I subtract, and what do I get? X to the 4th. And do you see a pattern here? The pattern here is that every single time I take another step in the long division, it's going to alternate the plus or minus sign, and it's going to leave me with x to the next larger power. Forever and ever and ever. This kind of pattern's never going to quit. And this is kind of an infinite sum. I could choose to write this as a power series. And this would be negative 1 raised to the power n times x to the power n. Yeah, cool. So if you tried to use the Taylor series formula, that's a little bit more difficult because taking derivatives of 1 divided by x plus 1 is going to require like the derivative quotient rule, and every single time you take another derivative, it's going to require you to do the quotient rule again, and it just gets really nasty when you take derivatives. So this is a shortcut method for discovering the same Maclaurin series where you don't have to do any derivative quotient rule. So I think that's nice. Again, we could also do this and see what it looks like on Desmos. This time we have -1 raised to the power n times x to the n. So check it out as we go from 1 term to 2 terms, 3 terms. As I increase the number of terms, it gets better and better. And notice this is different because unlike e to the x, where it was getting better and better over a larger interval, do you notice how it kind of looks like it's stuck, like it's hitting a wall exactly at x equals 1? And then once it just gets to that point, it just can't do better. It doesn't even matter if I add 100 terms. It's getting closer and closer to the wall, but it can't ever move past that. This is because that power series only has a radius of convergence of 1. It can converge from -1 to +1, but it has to diverge when it hits this point. So that power series is only good so far, and then it fails. Okay, find the Maclaurin series for each of the following functions. I like this example because it illustrates something neat. If I have 1 divided by x plus 1, that's this series right here. Right? We just discovered that together. Now what I need is 1 divided by x squared plus 1. All you have to do is look at your function and say, all I'm doing is I'm replacing x with x squared. So let me go to my power series. And I will just replace x with x squared. Done. And again, if you were to use the Taylor series formula, that would be such a pain in the butt, right? Like taking multiple derivative quotient rules of 1 over x squared plus 1, like that's going to get really nasty really fast. I wouldn't be able to even calculate like the first 3 terms of the Maclaurin series using the Taylor series formula just because it's like, I don't know, too yucky. But just using this quick little composition makes it super nice. Show you again on Desmos. If I have this adding up the first few terms of the power series, boop, 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 it's getting a better and better and better match up to a point. And then again, it doesn't even matter if I add 100 terms together. It still can't move past this, right? And the problem is the radius of convergence of the power series is still 1. And so you can see it's a really, really, really good approximation of this red function up to a point where it diverges. And the power series fails. It can't move past that. Okay, one more, arctangent. Well, we know that the antiderivative of 1 over x squared plus 1 is arctangent x plus a constant. So what if I just go back to my power series? Oops, no, stop. What if I go back to my power series that I had for 1 over x squared plus 1 and I just take the antiderivative of every single term here? it's going to be a constant plus looking at this power series and taking an antiderivative means I'm going to have x to the power what? 2n plus 1, and then I divide by 2n plus 1, right? So it'll be negative 1 to the n power divided by 2n plus 1. I do have, well, no, that's right. Okay, cool, that's it. Nice. And we could solve for what that constant is by plugging like x equals 0. And that constant will be 0 because arctangent of 0 is supposed to be 0. And if I plug in x equals 0, it goes to 0. So cool. That is the arctangent power series. Again, really, really tough to do if I were using the Taylor series formula, but there's shortcuts and there's ways around it to get what we want. Let me do this one more time. Nope. There we go. Cool, so I can get the same picture where I've got a better and better and better approximation of my function until it doesn't anymore, right? Because the radius of convergence is just 1. All right, explain how we represent complex numbers geometrically in the complex plane. So I'm shifting gears a little bit, but there's a reason. A complex plane has an imaginary axis and a real axis, where the real axis is like a real number line. The imaginary axis is like the imaginary number line, where it has all the imaginary numbers. And if I've got a complex number like 3 plus 4i, that would be 3 units in the real direction and 4 units in the imaginary direction. And I can put a spot on the plane, and this point represents the number 3 plus 4i, right? Probably seen that before. Well, what if I wanted to find the distance in this complex plane between 0 and the point 3 plus 4i? How do I find this distance? You're right that I'm going to use the Pythagorean theorem because I could draw a little right triangle like this. And this side of the triangle is 3, this side of the triangle has length 4, and the Pythagorean theorem says 3 squared plus 4 squared is going to be that straight line distance squared. And so my distance is going to be the square root of the real part squared plus the imaginary part squared. So that distance in the plane is 5. This is also how we define absolute value for complex numbers. Absolute value for a complex number is the distance in the complex plane that makes a straight line from 0 to the point. And it's still valid for real numbers, right? Because in a real number line, an absolute value is the distance from 0 to the point. But this is the generalization of absolute value for complex numbers. So in Calculus 2, what I would normally have the students do first is I would have them find the radius of convergence for a power series using what is called the ratio test formula and the root test formulas. We're not going to do that in this differential equations class. We're just going to move straight on to the more intuitive thing. Any point where a function fails to have like a power series representation, right? The point where it breaks down, any point where you don't have a value of your function, a finite number value, it's okay if it's complex, but it can't be infinity. And that's not true for all of the derivatives, right? You have to have a finite real or complex value for your first derivative, second derivative, third derivative, fourth derivative, and so on. If that ever fails, that point is called a singularity. The radius of convergence for your power series is actually just the distance from the center of your power series to the nearest singularity. Because your power series for your function is linked to the derivatives of your function by that Taylor series formula. So if the derivative doesn't exist and it's not a finite value, the Taylor series formula is telling you the power series can't describe it there. Well, if your derivative, or if your value of its function itself goes to infinity or negative infinity or some complex generalization of infinity, then your power series can't converge there. It diverges. And if a point diverges, then it implies that every other point in the complex plane that's farther away from the center must diverge as well. And so there's going to be a point where before that nearest singularity, things are converging, because why can't they converge? They should be able to converge. And every point inside that radius, inside that distance, is going to converge as well, because we kind of proved that earlier today. And then once we hit that singularity, every point farther away is going to diverge, because again, what we proved earlier in the lecture. So when we talk about radius of convergence, we're talking about this picture in the complex plane where maybe my power series is centered at 0. And maybe this is the nearest singularity of my function. And that means I have a radius of convergence of 5. And every single point, every single number in the complex plane that's inside this circle with radius 5, so that's centered at the center of my power series. I wish it wouldn't do that. I don't know how to make it not do the vertical line thing with my highlighter. But all of these complex numbers that fall inside this disk that's centered at the center of my power series with a radius of 5, all of those points are going to converge for my power series. You can do add, subtract, multiply, divide just the same way with complex numbers. And so we calculate the power series the same way with complex numbers. But all of these points are going to diverge when they're outside of my radius of convergence. So you get a little disk or a little circle. That defines the boundary between converging and diverging in the complex plane. All right, so if I were to determine the radius of convergence for the Taylor series of each function centered at each given point, let's say I want e to the x centered at c equals 0. This radius of convergence is infinity because I have no singularities anywhere in the complex plane. I guess you could say the point at infinity is a singularity in certain contexts. That's a whole thing for another day. But what about this? Do you notice any singularities that are happening with 1 divided by x plus 1?
Would there be one at x is negative 1?
Yes. We have a singularity at x equals -1, right? Because 1 divided by -1 plus 1 is 1 divided by 0, and this is not defined. If the value of my function is not defined there, we reached a singularity where I can't represent my function with a power series. The power series diverges, and every point farther away from that has to diverge as well. All the closer points are going to converge because, of course, they would. Why wouldn't they? But I only get the distance from the center at 0 to my singularity at -1. What's the distance? 1. So the radius of convergence must be 1, because that's the distance from the center of the power series to the nearest singularity. Alternatively, if I said that my center of my power series was the number 7, then what would my radius of convergence be? 8. So in this scenario, if the center was at 7, that power series would converge for numbers up to like 14.9, you know? But 14.9 would not converge in the case where the center of my power series was at 0. This would only converge for up to like 0.99, right? Okay. Determine the radius of convergence for the Taylor series of each function centered at each given point. Same question. What about 1 divided by x squared plus 1? Where are the singularities? There's 2 of them, and you're right, you've got 1. One of them is at I, because if I have I squared is -1. -1 plus 1 is 0, and I have an undefined part of my function. So that's one singularity. There's another one. Yes, -I. So in my complex plane, I've got my imaginary axis, and I've got my real axis. And here is a singularity at I, and here's another singularity at -I. If I were to have my power series centered at 0, what's my radius of convergence? The radius of convergence is the distance from the center to the nearest singularity. So when we talk about distance in the complex plane, what we do is we take the square root of the real part squared plus the imaginary part squared. And you don't worry about the i's, but right now what we're talking about is like the real part is 0 and the imaginary part is 1i, right? And so the distance is 1. In other words, the absolute value of I is 1. The absolute value of -I is 1. So anyways, the distance from this point to this point is 1. So my radius of convergence is 1. It's going to converge for all of the points inside this disk, and it's going to diverge for all of the points outside that disk. What if instead I chose a center for my power series at the point I don't know. I guess it doesn't matter. Let me choose a center at the point 2. What would my radius of convergence be? If this was my center, what's the difference, but what's the distance from my center to the nearest singularity? They're both equidistant, but you know.
Square root of 5.
Square root of 5, there you go. What's the radius of convergence for arctangent? Well, you might say, I don't know what the singularities of arctangent is, like, ugh. But remember that taking the antiderivative does not change the radius of convergence. The radius of convergence remains the same even when you take an antiderivative, and that means for arctangent you would still have the same radius of convergence as you do for the derivative of arctangent, which is 1 over x squared plus 1. Okay. That is my super fast review of like 3 different Calculus 2 lectures crammed into one differential equations lecture, because we don't need to know all of the details of power series, but I want you to remember kind of what the deal is with power series before we start solving differential equations. Remember, you calculate a power series by taking the limit of the partial sums of its terms. On a computer, that means like you just do a loop, a for loop, and you add up terms in every iteration of the loop, and you do it as many times as you need to get an arbitrary degree of precision, however precise you want to be. And then one thing to be careful with as we solve differential equations with power series is that your solution might have a finite radius of convergence. Maybe your power series is a solution to the differential equation, but keep in mind it might be limited in how far it can predict into the future, because even though the true solution to the differential equation might continue into the future indefinitely, your power series might describe that solution really, really well until it hits the end of its interval of convergence, and then it diverges wildly. Well, it's not because your solution's wrong, it's just because it hits that wall, and that's just a mathematical fact that we can't get around. But I'm looking forward to Monday, because I think it's actually kind of fun to find these power series solutions when we actually talk about the differential equations part.